All right, let's get right into it. We all know we need oxygen to live, right? But have you ever really stopped to think about the microscopic delivery service that makes it all happen? Today, we're taking a deep dive into the incredible molecular machine known as hemoglobin. It's not just about picking up a package from the lungs. The real genius, the absolute magic of hemoglobin, is its uncanny ability to know exactly where in your body that package of oxygen is needed most desperately. So the big question is, how on earth does it do that? To really get what makes hemoglobin so special, we first have to understand the problem it's solving. And trust me, it's a massive logistical challenge, happening trillions of times a second inside you right now. And this right here is the most important part. I mean, think about it. A delivery truck that just drives around with packages but never opens its doors is completely useless, right? Hemoglobin has to be a master of both, holding on super tight to oxygen in the lungs and then letting it go easily in the tissues that need it, like your muscles when you're going for a run. So how does it know the difference between your lungs and, say, your big toe? Well, it acts like a tiny, incredibly smart sensor. It's constantly reading the chemical clues in its immediate environment. So when your muscles are working hard, they're not just burning through oxygen, they're also making waste. You can think of it like metabolic exhaust. And the two main byproducts are carbon dioxide and acid. These act like a chemical flare, basically shooting up a signal that says, hey, we're over here, we need oxygen now. And this brilliant little mechanism actually has a name, the Bohr Effect. It was discovered way back in 1904 by a Danish physiologist named Christian Bohr. And it's really the core principle here. All it means is that wherever there's more acid and CO2, hemoglobin's grip on oxygen just loosens. This table really shows you hemoglobin's double life perfectly. In the lungs, it's all high oxygen, low acid. Its job? Grab that oxygen and don't let go. But then it travels to your working muscles, where the environment is the total opposite, low oxygen and high acid. And just like that, its job completely flips. It's time to release that oxygen. And get this, hemoglobin isn't just a delivery truck, it's also the cleanup crew. After it drops off the oxygen, it actually picks up a huge chunk of that acid and CO2 to haul it away from the tissues. It's a seriously efficient two-way system. Okay, so we've seen hemoglobin can handle the daily grind of exercise. But what about a more extreme challenge? What happens when the air itself just has less oxygen, like when you're way up at a high altitude? Well, the body has this incredible secret weapon. It starts producing more of a special molecule called 2,3-bisphosphoglycerate. Yeah, that's a mouthful, so we're just going to call it BPG. Think of BPG as the master regulator that fine-tunes hemoglobin's performance when things get tough. So BPG works by binding right onto the hemoglobin molecule, but it doesn't bind where the oxygen does. Instead, it wedges itself into this little cavity in the center. And when it does that, it basically locks hemoglobin into a shape that has a lower attraction for oxygen. It's like it's prying hemoglobin's fingers open, forcing it to let the oxygen go more easily. And you can see exactly how this works right here. On the left, that's the T state, which is hemoglobin without oxygen. See that perfect little pocket where BPG can just slide right in? Now look at the right. That's the R state, when hemoglobin is full of oxygen. The whole structure changes, and that pocket for BPG is just gone. It's a brilliant physical trick that guarantees BPG only works when oxygen needs to be kicked off. This timeline really shows how fast and dynamic this whole system is. At sea level, everything's humming along just fine. But then you go up to a high altitude, and suddenly your oxygen delivery takes a nosedive. But within just a few hours, your body starts cranking out more BPG. This extra BPG forces hemoglobin to give up more of the oxygen it's carrying, which brings the delivery rate right back up to a functional level. It is a rapid, life-saving adaptation. And here is the payoff. Thanks to this BPG adjustment, your body can restore oxygen delivery to nearly 40% of its total capacity. That's almost as efficient as you are at sea level. It's just a stunning feat of molecular engineering that lets us survive in thin air. So hemoglobin is this incredibly complex, finely tuned machine. But that also means that even one tiny error in its blueprint can lead to absolutely catastrophic consequences. I mean, just look at how specific this is. The entire devastating disease of sickle cell anemia comes down to a single mistake in a chain of hundreds of building blocks. At just one spot, position number 6, a negatively charged glutamate gets swapped for an uncharged valine. That's it. One tiny change. But that one change is just devastating. Swapping in that valine creates a sticky spot on the outside of the hemoglobin molecule. It's a patch that hates being exposed to the watery environment inside the cell. And this is what happens. On the left, you see healthy, round red blood cells. They're flexible, they can squeeze through the tiniest blood vessels. On the right, you see the sickled cells. Deformed, rigid, crescent-shaped, all because of that one sticky patch. So how does this actually happen? Well, when someone with sickle cell is in a low oxygen situation, like during heavy exercise, their hemoglobin lets go of its oxygen. That action exposes that sticky valine patch, and that patch immediately starts looking for a place to hide, finding a complementary spot on another hemoglobin molecule. And that sets off a terrible chain reaction. Molecule sticks to molecule, and they start forming these long, abnormal chains, almost like tiny, damaging ropes inside the red blood cell. These ropes then bundle together, forming these massive, rigid, insoluble fibers. And it's these fibers that physically push against the inside of the cell membrane, forcing the whole red blood cell into that warped sickle shape. The medical consequences are just awful. The rigid cells are fragile, so they break apart easily, causing anemia. They get stuck in tiny capillaries, blocking blood flow. This causes excruciating pain, organ damage, and all the other debilitating symptoms of the disease. You know, this quote from our source material really says it all. There is probably no better or more tragic example of how absolutely critical the precise sequence of a protein is for its function and for our health. A single atom out of place, and it changes everything. The whole thing, this entire complex dance of sensing the environment, adapting to thin air, delivering and cleaning up, it's all coordinated by one single protein. It really makes you wonder, what other incredible molecular ballets are taking place inside of you right this very second?